The bird doesn't want to get hit. He's not going in the opposite direction. All right, so I'm gonna start working on mine. If you didn't quite finish, feel free to keep working on it. I'm gonna start with my picture though, and then I'm gonna want, even if you're not done, I'm gonna want your attention by the time I get to the end of my picture. All right, so Mr. Fusco is luging. We said that that's the one where your feet first, right? So there's his legs, and he's moving this way, right? And then he's making sound. So the sound in front of his face is getting bunched together, the higher frequency, right, shorter wavelength, and the sound behind his face is getting spread out. So lower frequency, longer wavelength. And then we have this owl over here that was, I don't know, trying to get some dinner or something, and hears or sees Mr. Fusco coming, so tries to fly out of the way. But no, he doesn't want to get hit, so he doesn't fly towards Mr. Fusco, he flies away. Maybe if he was smart, he would have flied perpendicular, but wasn't smart. So moving in the same direction. All right, so the source of the sound is Mr. Fusco, and he's traveling at 68 meters per second. Now I called the way he was moving positive, right? So I called that way my positive direction, so that velocity was positive 68. The detector is the owl, right? And the detector is moving at 25 meters per second, also in the positive direction. And then the sound itself, the sound that the owl is hearing, right, is also moving in that same direction. So yeah, I had positive for all three of those velocities. Follow-up questions from anybody about all three of those being the same direction. All right, and then the frequency that's emitted was the 482 hertz, right? And we want to hear the frequency that the owl detects. Right, so we're using the exact same version of the Doppler effect equation that we've seen for everything else. Right, where we have our 482 as the emitted frequency, and then we have positive 343 minus positive 25, and positive 343 minus positive 68. We bet the owl better hear something that is still higher frequency than 482, because even though they're moving in the same direction, right, the waves are going to still be a little bit more bunched together when the owl hears them than when they were emitted, right? And that's because the owl's moving slower than the source. So I had positive 318 as my numerator and positive 275 as my denominator. That's good because I need that ratio to be greater than 1 if we are going to hear a higher frequency. And then I got 557 hertz for what the owl hears, right? These both have a ones place, that's significant, so when I subtract them, that's precise to the ones. These both have a ones place, so that's also precise to the ones. So when I divide these now, that answer should have 3 significant digits, and this has 3 also. So I know some of you are struggling with the significant digits on that. Follow-up questions about Mr. Fusco and the owl? All right, I think I will make a mental note to have us do one more of those for homework. All right, so now just kind of finishing up with the Doppler effect. There are a number of different technologies that incorporate this shifting of frequencies and wavelengths. One of them, I think some of us were keeping tabs on last night, maybe even this morning. What's that? Yeah, so like weather people, right? Use something called Doppler radar that actually is named correctly. Right? That does utilize the Doppler effect. So that is one example. Another one is the radar guns that the police use to kind of catch you speeding, right? So they reflect, I think it's microwaves off of you. And then the same thing that emits the microwaves, like listens for them to reflect back to you. And based on that shifting of that wavelength, right, we know the velocity of you. As we just said, Doppler radar does the same thing. So we have some sort of like tower that emits radio waves, right? And we know the frequency that it's emitting them at. And then what would those waves get reflected off of that we want to know about? Ben? What? Yeah, the weather systems, so probably clouds, right? So just like storm systems, maybe it's a cloud, maybe it's just a different temperature mass of air, right? So based on the shift in pitch and wavelength as the waves reflect off of that and then come back, we know how fast that's moving, and we'll know when that system will reach someplace else based on how fast it's going now. We can use Doppler effect to do blood flow analyses, so we can shift like ultrasound waves, for instance, off of blood and know how fast the blood is moving, right? Sometimes we want to know that. We mentioned ultrasound earlier for imaging, fetuses. We also use the Doppler effect to listen to the heartbeat of a fetus. So like when my son was inside my wife, we got to hear his heartbeat like from a really young age, because the ultrasound machine reflected these ultrasound waves off of him, probably hopefully his chest or back or some large area that is beating with his heartbeat. And then based on that shift in wavelength coming back, right, we know the rate that the heart is beating, and the device, of course, makes it sound like a heartbeat. Otherwise, it wouldn't be too dramatic. And then the final example I have for you guys is in determining how far away, like super far, astronomical things are. So we had that in the one homework problem where we were looking at the Doppler shift of light off of distant galaxies to know how fast they were moving relative to us. So that's a pretty important use of the Doppler effect as well. Follow-up questions on any of these, and then I have one other application before we move on. All right, did we talk, I think we had to, did we talk earlier this year about like how many planets we know about? We did. All right, well, how many planets are there?
You mean our solar system?
Oh, I don't know, not necessarily. Fine, let's start there. How many planets are in our solar system? Is it 8? I think it's 8. There's like Mercury, Venus, Earth, Mars, Jupiter, Saturn, Neptune, Uranus, right? I think that's it. We got 8 here. And then, then how many like in other solar systems? Well, infinite might actually be a good answer. But confirmed, like scientifically accepted. Like hundreds, right? I think like 300 something by the strictest criteria to confirm something. But really we have like thousands of well-accepted planet candidates that just haven't met that threshold of calling them like official yet. And there are 2 main ways that those planets have been discovered. We haven't like actually like used the telescope to see any of them at all. They're just too far away. There's not enough light. All we see, even if we could see it, would be the light from their star, right? We can't see them. So there's 2 main ways that we use to view these thousands of planet candidates. And one of those ways involves the Doppler effect. All right? So our sun, right, does, kind of, let me draw our galaxy if I dare to. I should have had a photo ready to go, then I wouldn't have to have drawn it. But we have like a spiral galaxy, so we're definitely going to have like spiral arms that come off. So that's terrible, but something like that. And so we're out here, so our sun certainly is like, which way would it be? Is orbiting around our galaxy, but from one reference frame, our sun kind of is sort of motionless, right? From one reference frame. However, it's not motionless, because things are pulling on it. So who's somebody that's pulling on the sun pretty strongly? Yeah, somebody more locally then. Us, fine. So we have these 8 planets that we just talked about, so maybe Mercury's over here, maybe Venus is over here, maybe the Earth is over here. And if the Earth is over here, I mean, we know that the sun pulls on the Earth because we're centripetally accelerating, like around the sun, right? But Newton's third law tells us that if the sun pulls on the Earth pulls on the sun just as strongly. Right? So there would be an equally strong force pulling the sun out this way. That would be due to the Earth. And what does the Earth do in response to that net force? Starts with A. Accelerates, right? Centripetally accelerates, but whatever, it accelerates. What does the sun do in response to the Earth's pull? It also accelerates. It does rotate, but not due to us. So the sun will accelerate due to the Earth. But then there's other things pulling on the sun also, like for instance, I don't know, maybe big fat Jupiter is like all the way out here. So that's going to be, even though it's further away, right? Jupiter pulls more strongly on the sun than we do. Right, so the net effect of this is that the sun like moves back and forth in response to all of the things that are pulling on it, right? And we can get a good measure of that velocity that it's moving, back and forth at, of that acceleration even, by looking at the light that the sun emits and detecting that Doppler shift, all right? So we can do that for our sun, but we can also do it for other stars. We can look at it, right, analyze the frequencies of light that are being emitted, and then based on the period of that wobbling, right, know what the orbital period of things orbiting around it, pulling on it are. So we've detected about half of the exoplanets, right, planets outside our solar system that we know about, by this Doppler method of looking at the light and looking at frequency shifts to know. We could know the acceleration, but unless we know the mass of that star or the mass of the thing pulling on it, we can't actually know how big the planet is. But based on the shift in the light itself, we know what the period of that planet is. So that we found about half the exoplanets that way. Anybody know the other way that we found, like the other half? Nah? So the other way is actually simpler. We get a little less data from it, but the other way is a little simpler. So here's the sun. And who are the planets that are closer to the sun than us? Yeah, Mercury and Venus. Who do we want to pick on?
Mercury.
Fine, Mercury. All right. So Mercury goes around the sun, and we can see Mercury sometimes, not too often, but every once in a while, right? Mercury is directly in between us and the sun, right? So if we were looking at the sun, which is a terrible idea, right? We might actually be able to see like a black spot that kind of moves across the sun, which would that's called the transiting, right? So Mercury is transiting in front of the sun. And does more light or less light from the sun reach us if Mercury's in front of it? Less light. And it should be a very predictable amount less light, right, based on the size of Mercury. So this is called the transit method of exoplanet detection, and we can look at a faraway star also. Now we won't be able to see like a hole moving across it if it's far away, but we can detect a change in how much total light is emitted by the star. And if we see periodic trends, like if it's, I don't know, I think Mercury goes around the sun like once every like 30-something days or 20-something days or 40-something days, something like that. So if we were analyzing light from the sun, right, as a function of time, and we saw that like every 20-something days, the brightness of it actually wouldn't look like that. Every 20-something days, the brightness of the sun dipped real quick and then went back to its original value, and 20-something days later, same thing, and 20-something days later, same thing, 20 days something later, same thing, right? We can identify that as a planet or something transiting in front of the star. So that's how we found like the other, half of the exoplanets, is by finding these dips in the brightness. And if you like that, the first Zooniverse site that I spent a lot of time on was called Planet Hunters, and you're actually searching for those dips in brightness. So anyway, the Doppler effect is not involved with the transiting method, but it is involved in the other way that we found planets. That's what I have for you guys in terms of Doppler effect. So again, right, the Doppler effect is a phenomenon involving all types of waves if either the source of the waves is moving or the detector of the waves is moving, right? In either case, we do have a Doppler shifting of the waves. However, right, only the waves in front of and behind the source get shifted. The waves like next to them don't get shifted at all. They would be the real frequency. That's why when we listen to like the trains and stuff, we said there was a brief instant where you should be able to hear the real pitch of the sound. All right, other issues from anybody about this shifting of frequency and wavelength if we have a moving source or a moving detector? Okay, fantastic. So the next thing we want to do is start talking about light. And then most of the rest of the marking period, we are really going to be narrowing our